Good morning, everyone. Welcome back to the My Tutor Online School. Hope you had a lovely evening, and it's really good to see lots of you joining us already this morning. We have a GCSE Chemistry session at 9:45 today, and that is on fractional distillation, paper chromatography, and noble gases. So really looking forward to getting stuck in. As always, our chemistry sessions are led by our tutor Aman, who studies medicine at King's College London. And if you have tuned in for the sessions we've had before, then you know lots about Aman already. Just to say from me that these sessions are an hour, so if you're new, you can expect 45 minutes of teaching from Aman and then 15 minutes at the end for any questions. If you have questions as the session is going on, then feel free to send them through the chat function or through the Q&A function, and we'll be able to pick up some of the questions. Just before we get started, quite a few people have already asked what will be happening today in terms of English that didn't go ahead yesterday. And someone has asked if maths will be cancelled to make up for the English session. So maths won't be cancelled, English will be happening. So today you will have an English session right after this session at 11 o'clock, and then you'll also have your normal math session at 12:15. So there won't be any cancellations. It will all be going ahead as normal. Cool, so I'm just going to hand over to Aman now to lead the session.
Hi everyone, welcome back. So as Frederica said, today we're going to be looking at more kind of separation techniques. So we looked at distillation, simple distillation yesterday, crystallization and filtration. So I thought we'd just do an exam question that we didn't manage to do yesterday, just to kind of tie that topic up, and then we'll do the other two types of separation techniques before going into the periodic table, which we'll be doing for the rest of the week. So in this question, we're being asked to describe a method for making pure crystals, that is a key word there, crystals, of magnesium chloride from magnesium and dilute hydrochloric acid. In this method, you should name the apparatus you will use, and you do not need to mention safety. So does anyone have any ideas how we make crystals from magnesium chloride dissolved into hydrochloric acid? Does anyone know? Thinking about what we did yesterday. Yep, excellent. So filtration, then crystallization, that's really good. So whenever we add kind of a metal, so we know magnesium is a metal, to hydrochloric acid, so to some kind of solution, we want to first filter. So although it says in the question that we're going to form crystals, so we know that then that means magnesium does dissolve in the hydrochloric acid, because remember, filtration is to remove insoluble substances. This suggests that we want to form crystals, so that suggests that magnesium does dissolve and is therefore soluble. But often when we add metals to solutions, there might be some excess metal that then doesn't dissolve, or there may be some impurities in there that we then have to filter. So we start by adding the magnesium to the hydrochloric acid, and we filter off any excess or any impurities. And once we've done that filtration, we'll be left with a filtrate, and in our filtrate will be magnesium dissolved into hydrochloric acid, making magnesium chloride. Within the excess of hydrochloric acid. And then if we want to just form the crystals, again, we do what we just decided yesterday, which was crystallization. So does anyone remember what the process of crystallization is, what the key apparatus is that we use? And some of the key things that examiners are looking for with crystallization. Does anyone remember what they are? Yes, excellent. So we've got a Bunsen burner, evaporating dish, really good. So we're going to heat up our evaporating dish on a water bath. So remember yesterday, we had a diagram. So remember, our evaporating dish will look something like this. We'll have a beaker with water inside it. So this is our water bath. And then we heat up our water bath. And does anyone remember why we heat it up on a water bath and not just heat up that evaporating dish directly? What's the key thing about crystallization that we like to do when we're heating it up? Yep, so we're evaporating water. So in this case, we'd be evaporating hydrochloric acid. So we're evaporating excess hydrochloric acid. And the reason we use it on a water bath is because if we heated that evaporating dish directly, it would evaporate too much of that hydrochloric acid. And some of you may remember that when we're trying to form crystals, we stop just when crystals begin to form. We don't wait for all the crystals to form. We stop when they just start crystallizing. And then what happens once we stop crystallizing? What do we do for the rest of the process? So we've heated it up, some of that hydrochloric acid has evaporated, we've got a few crystals forming in our evaporating dish. So over here, we've got a few crystals forming. What do we do next? What's the last stage? Yeah, we leave it, we use a Petri dish. Excellent, very well done, everyone. So we use a Petri dish. Why do we use a Petri dish? What was the reason for using a Petri dish? I know a lot of you were asking questions about that yesterday. Does anyone remember what the reason was? Excellent, it has a large surface area. So what we do is we leave it, we take what's in that in the evaporating dish, and we put it into a Petri dish because that has a larger surface area, and that means that any remaining hydrochloric acid can then evaporate from that surface. Excellent, very well done. So that's how we would answer that question. So starting with filtration and then the crystallization. Really, really well done, everyone. Okay. So now let's move on to fractional distillation. So we looked at simple distillation yesterday, and now we're going to look at fractional distillation, specifically with ethanol and water. So there are two examples that all the exam boards want you to know with fractional distillation. The main one is crude oil. We won't be looking at crude oil today because that's part of a different topic, but that does involve fractional distillation and a process called cracking. But we'll be looking at ethanol and water today. So the first thing, why do we do fractional distillation? Well, we do it to separate a mixture of miscible liquids. And what does miscible mean? It means that the liquids dissolve in one another. So for example, if you imagine you add oil to water, we know that the oil will form a layer on that water, so they are not miscible. They don't dissolve within one another. But ethanol and water, if we add those together, they do dissolve. So that means we can separate them using fractional distillation. Someone's asking, can you write that definition down? Yes, of course. So miscible just means that the liquids can dissolve within one another. So dissolve within one another. Okay, so why do we do fractional distillation then? So we know that they separate a mixture of miscible liquids, but you might be thinking, well, why can't we just use simple distillation? Because simple distillation can also do the same thing. Does anyone know? Why do we not use simple distillation? What's the advantage of using fractional distillation for separating ethanol from water? Okay, so no one's really answered that question. That's okay. So someone has said there are different boiling points. That's excellent. So that is one of the main things, actually. There are different boiling points. So in the cases of ethanol and water, ethanol has a lower boiling point than water. So what that means is when we heat up this flask, which let's say it has ethanol and water in it, the ethanol will evaporate first. And the key part of apparatus in a fractional distillation method is this fractionating column. Now, this can be a bit confusing about what happens in this fractionating column. But in this fractionating column, we have glass beads. And these glass beads are at different temperatures. And what that means is that when the ethanol evaporates off, remember, ethanol's got a lower boiling point, so that means it will evaporate first. It will enter this fractionating column. And the fractionating column is hotter at the bottom of the column and cooler at the top. So that means the ethanol will rise up, and eventually it will become a gas, or sorry, a liquid. It will start becoming a liquid because it will cool down. And then we go into the condenser, and in the condenser it will fully become a liquid before dripping in. Now you may be thinking, but why? What happens to the water then? Surely the water also evaporates. Well, it does. But the reason we use a fractional distillation method rather than simple distillation is because of this fractionating column. Because we know that the boiling point of ethanol is around 78 degrees. You don't need to know this, but it is about 78 degrees. You do need to know that the boiling point of water, though, is 100 degrees. So if we're boiling, or our Bunsen burner is at a temperature of about 85, we would expect all of the ethanol to evaporate, but potentially some of that water might start evaporating. And the reason for that is that we know that the water, when something reaches its boiling point, Before it starts boiling, it evaporates. So remember last week we covered the difference between evaporation and boiling. So evaporation happens before the boiling point, and it's when some of those liquid particles come to the surface and they start evaporating, so start becoming a gas. Whereas boiling is at a certain temperature and the whole liquid becomes a gas. So at 85 degrees, some of the water will start becoming a gas, and it will go into this fractionating column. But the reason it doesn't reach that condenser is because it has a higher boiling point than ethanol. So in the fractionating column, where it's hotter at the bottom, that means as it starts going up, the water will start cooling before the ethanol does, and instead will drip back into the flask, because when it cools, it becomes a liquid. So let's say the ethanol, because it's got a lower boiling point, starts cooling here. Because it's over halfway, approximately, it will eventually end up in the condenser. Whereas if the water starts cooling here, because it's got a higher boiling point, that means, due to gravity, it will drip back into that flask. So the reason we use a fractionating column is because it's easier to separate two liquids. In simple distillation, there's no fractionating column there. So if we were heating our mixture at 85 degrees, we'd end up with both water and ethanol in here. So the reason is that in fractional distillation, we form a purer sample of just ethanol. So I'm just going to summarize that again, because I can understand that's quite complicated. So we're heating up a mixture over here in our round bottom flask of ethanol and water. Ethanol has a lower boiling point, which means that it evaporates before water. And when it evaporates, it reaches this fractionating column, which is hotter at the bottom of the column and cooler at the top. It will start condensing nearer the top because it has a low boiling point. And when it condenses near the top, it will go into this condenser and it will all condense into a liquid and drip into this beaker. Whereas water, even though it might start evaporating, it will go into this fractionating column, and because it has a high boiling point, it will condense lower down the fractionating column. And that means that it drips back into the round bottom flask. So that's how we separate both water and ethanol using fractional distillation. Someone's asking me, how can you control the temperature of the Bunsen burner? It's a very good question. You can't really, but what some people do is in the fractional distillation column, they add a thermometer. So you can see the temperature in the round bottom flask. So you add it in and it goes all the way into that round bottom flask. So you may have done that at school. If not, you will tend to add a thermometer, especially when you're separating two liquids, because you do need to know what the temperature is. Someone's asking, would you keep repeating the experiment until you have the purest sample possible? You can do, but eventually if your temperature rises too high, then you'll start getting water in this beaker, and we don't want that. So usually you keep it at one temperature and you keep going until you feel that all the ethanol has basically been separated from the water. Okay, the next technique that we're coming on to then is paper chromatography. And hopefully some of you have had a go at this at school. It was one of my favorite experiments. It's really fun. So what we do is we have a piece of filter paper, and it is usually filter paper that we use for paper chromatography, and you add a line to the bottom of the filter paper. So here it's called the baseline. Does anyone know why we draw that line in pencil and not in ink and not in pen? Why do we draw that baseline in pencil? Yep, smudges. Ink is soluble in water. Yep, so the main thing is that if we add ink, if this line is drawn in ink, and what will happen is it will either smudge or dissolve in the water or the solvent. So very well done, everyone. So we use a pencil line. Now, why do we use paper chromatography? What's it for? So it's for separating substances from mixtures in a solution. So things like dyes, it's used a lot in forensics as well. So for example, if you've got a message written in a certain pen and you don't know which pen was used to write that message, and you have 3 pens and you're trying to decide which pen, you could use paper chromatography to have a look at which inks are in those 3 pens and see which one matches with the original ink in a message. So just like here, we've got a mixture and we've got these 3 dyes, and we're trying to work out in this mixture which dyes are in that mixture, and we can see the mixture is formed from dye 1 and dye 3. So you can see, because that matches up here and it matches up here. So the mixture is formed of dye 1 and dye 3. So in a lot of exam questions, it's just about interpreting what the chromatogram shows you. We'll do some exam questions later and have a look at those questions. And then the other thing that is important to know is that the further up the paper the substance travels, the more soluble it is. So for example, dye 3 travels a lot further up than, dye 3 travels a lot further up than dye 1. So that means dye 3 is more soluble than dye 1. And that's because it travels further up the paper. One thing that you may be asked to calculate in the exam is something called RF, which is the retention factor. And that is basically the distance travelled by the substance. So let's say the distance travelled by this blue one here, so dye 1, divided by the solvent front. So the solvent front is how far the solvent travels up the paper. So if it travels to here, that's the furthest it travels, that's the solvent front. And we do how far the dye travelled divided by the solvent front, and that gives you a retention factor. And basically, the higher the retention factor, the more soluble a substance is. Does anyone know why we keep the solvent below the pencil line? Why when we submerge that in, we always keep it below the solvent line or the pencil line? Yep, someone said it would dissolve into the solvent. So actually what would happen is it's to do with these dots of dye. So if the solvent reaches the dots of dye, they would just dissolve in that solvent, and we don't want that. We want the paper to take up that solvent and allow the dyes to travel. So it's about not allowing these dyes to dissolve in that solvent. And the final point on this slide says that we use a detecting agent if the substances in a mixture are not coloured. So I've seen this in a lot of the syllabuses as well. So a detecting agent is added. So if something is colourless and you want to use paper chromatography, you can use a detecting agent just to distinguish all the colours in there, which is sometimes added, and it won't affect the experiment. Do we need to know about gas chromatography? So that's more of an A-level topic, but yes, it can come up in the AQA syllabus. I don't think it's in the OCR syllabus, but I'm pretty sure it's in the AQA and the EdXL syllabus. Can you use normal paper? No, so we tend to use filter paper because of the properties of that paper. Normal paper, I mean, you can use it, it wouldn't be as effective. Usually it's filter paper that the examiners are looking for if they ask you a question on it, and at school you'll tend to use filter paper as well. Okay, so that kind of brings us to the end of separating mixtures. Before we go on to looking at the periodic table and starting on the noble gases, does anyone have any questions about paper chromatography or fractional distillation? Someone's asking, can you explain what the retention factor is again? Yep, so the retention factor is about how soluble a substance is. So remember I said that if something moves further up the paper, that means it's more soluble than something that moves less far up the paper. So dye 1 here is less soluble than dye 3. And the retention factor is just about putting a numerical value on that. So to calculate that, they will always give you the formula in the exam. It's about how far the dye travelled. So for dye 1, it's how far it travelled, divided by the solvent front. So how far this water travelled up the paper. So if the watermarks finish here, that means it travelled up this far. So we do how far the dye travelled divided by the solvent front. Does the RF have a unit? No, it's just a numerical value. I'm doing EdXL and I've never learned about gas chromatography. Sorry, I must have got that confused then. It must be OCR that has it and EdXL that doesn't. As I said, it's more of an A-level topic, so it probably comes up right at the end of a paper as a grade 8 or grade 9. Can you do an example of RF? Yes, we will do one in an exam paper question later. What if the pen is white? So I said this before, so if we've got something that's colourless, we can add a detecting agent to it and that will add colours to it. Okay, let's move on to the periodic table. So before we start looking exactly at the periodic table, it's important that we know what a period is and what a group is. So a lot of people were asking me last week the difference between them. So the groups will be on the top and they will say the number of electrons in the outer shell. So if we're in group 1, that means an element has 1 electron in the outer shell. If we're in group 7, that means it has 7 electrons in the outer shell. And periods are the rows, and they basically have increasing atomic numbers. Okay, so let's have a look at the periodic table. So over the next couple of days, we'll be looking at the transition elements. The noble gases we'll be looking at today, group 1 and group 7. So all the exam boards require you to know about group 1, group 7 and the noble gases. Some of them require you to know about the transition elements as well. And remember, I've talked about this zigzag line before. That's the difference between metals and non-metals. You don't need to know where it is, but if you have a rough idea, that can be helpful in the exam. So we'll be looking at the different properties of each of these elements and why they have those properties. But today we'll be looking specifically at the noble gases. So the noble gases are group 0, sometimes denoted as group 8. And as we can see, they are non-metals. They're on the right-hand side of that green zigzag line, and they are very unreactive. So let's have a look at why they have these properties then. So these are kind of the properties that most exam boards want you to know. And you need to be able to explain why. So someone is saying, does noble mean non-reactive? Yes, it is to do with the fact that they are non-reactive. Very well done. So we'll start off first with the fact that they have a complete outer shell of electrons. So to show you that, I'll draw the electron structure of neon. So neon is the second noble gas, and it's got an atomic number of 10. That means it has 10 protons, and remember, the number of protons is equal to the number of electrons as long as something isn't charged. So if it has 10 electrons, 2 in the first shell, remember the maximum capacity of the first shell is 2, and 8 in the second shell, and remember the maximum capacity of the second shell is 8. So 2 plus 8 is 10. So that's the electron configuration of neon. And what we can see is that its second shell is complete. That means it has a full outer shell of electrons, and all the noble gases have a complete outer shell of electrons, and most of its properties stem from that. So we know that metals, for example, so sodium, will have 1 electron in its outer shell, and the halogens, so something like chlorine in group 7, will have 7 electrons in its outer shell. So what does that mean? It means that sodium likes to lose an electron to get its full outer shell, and chlorine likes to gain an electron to get its full outer shell. And that is called reacting. So remember, when sodium loses its electron, it's usually forming some kind of ionic bond or a metallic bond to form an ion, and therefore it's reacting with something else. Same with chlorine. To gain that electron, it's either undergoing covalent bonding, so it's reacting, or forming an ionic bond, again, reacting. So what that means is, if neon has no electrons to share, gain, or lose, it doesn't react. And that is why the noble gases are non-reactive. It's because they have this full outer shell of electrons, and so there are no electrons mobile to be used in any reactions. The other thing is that they are single atoms. So if, for example, we know that neon has a full outer shell of electrons, it's not going to form a covalent bond with another neon atom. So remember, for example, chlorine. We know chlorine goes around in pairs because that means it can share its electron with another chlorine. So for example, it can share its electron with another chlorine and they would both have 8. So remember covalent bonding, and we did that last week. Whereas with neon, because it's got its full outer shell, it doesn't share any electrons. So that means it goes around as a single atom. And you may remember we talked about intermolecular forces last week, and I know a lot of people were getting confused between covalent bonding and intermolecular forces. But what we know is that in neon, there's no covalent bonding because it doesn't bond with any other non-metal. So what that means is, as neon is a gas, it goes around with intermolecular forces between atoms of neon. And so that is also why the boiling point is really low. So you may remember intermolecular forces are very weak. So that means that the boiling point of neon is very low. So this is group 0, the noble gases. Okay, so we've talked about them not being able to react because of their outer shell. That also means they're not flammable. So remember, something being flammable is about something being able to catch on fire or combust. So it's a reaction. If they don't react, they can't catch on fire. We've said the boiling points are low because of the weak intermolecular forces, but we need to know that they increase down the group. So does anyone have any idea why the boiling points increase down the group of the noble gases? So why is the boiling point of radon higher than the boiling point of helium? Does anyone have any ideas? Now remember, boiling points relate to the intermolecular forces. Excellent. So the atoms increase in size as you go down. So what that means is that because they increase in size, remember, intermolecular forces get larger as the atoms get larger. So in the case of radon, it's a lot bigger than helium. And so therefore, because it's bigger, that atomic mass is bigger. So instead of saying it's bigger, it's better to say that the atomic mass is more. And therefore, there are stronger intermolecular forces. Someone said there's more electrons in the outer shell. That's not correct. Remember that the outer shell will always be complete, so there won't always be more electrons as such. Although you might think that the fifth or sixth shell will have more electrons, it's still a complete outer shell. So that doesn't mean that there's more energy. It's nothing to do with the electrons. It's to do with the intermolecular forces between the atoms getting bigger because of the mass of each atom increasing. So yeah, there are more shells. So the key answer that examiners will be looking for is that the mass, the relative atomic mass, gets bigger as we go down that group, and therefore the intermolecular forces between the atoms get stronger. And so more energy is needed to overcome them. The next one is density. So does anyone know the equation for density? You might know this from physics. What is density equal to? Yep, density equals mass over volume. Excellent. So because density equals mass over volume, remember most gases have quite a low density. Because they've got quite a low mass in a fixed volume. So density, if you think about the particles in gases, because they're not fixed, that often means that they can have quite a large volume. So if you imagine our gas particles, remember they've got to be in a closed container, they're quite far apart. So they can have quite a large volume, but quite a small mass. So if you imagine if the mass is only 1, but the volume is 5, that means our density would be 0.2. Whereas if the mass increases, but the volume stays the same, so let's say the mass goes up to 3, but the volume stays the same, that means our density goes up to 0.6. And that is why the density increases down the group. So we talked about the mass increasing, the relative atomic mass increasing down the group, but the volume pretty much stays the same for a gas. So because that mass increases more than the volume does, that means the densities are low, but they increase down the group. So we've said that noble gases have a complete outer shell of electrons. That makes them unreactive and therefore not flammable. They go around as single atoms because they have a complete outer shell of electrons and so don't need to share any electrons. And that also means that they have intermolecular forces between those atoms that are very weak. Those weak intermolecular forces require very little energy to overcome. So that means that their boiling points are low. Note here that I haven't said melting points, I've said boiling. Why have I said boiling and not melting? Does anyone know why have I said boiling, not melting? They are gases. Excellent. So because they are gases, remember that they are gases at room temperature. So that must mean that their boiling points are low. It's not about their melting points. It's about their boiling points. Someone's asking, can we call them group 8? Yep, I said earlier that they can be also denoted as group 8. So group 0, group 8, it means the same thing. So their boiling points are low and they increase down the group because the atomic mass increases down the group and the densities are also low. Density equals mass over volume. But again, that increases down the group because the atomic mass increases down the group and the mass increases more than the volume. So therefore the density increases down the group. Okay, so that's all the properties we need to know about noble gases. So now let's just think about some of their uses. So one of the ones that you may have heard of is helium being used in balloons. Does anyone know why helium's used in balloons? What's the special property of helium? Well, it's to do with the properties we've just talked about. Does anyone know what's... Yep, so people are saying it's lighter than air. So exactly, so the correct term is it's less dense than air. So that means because it's less dense than air, it rises. And that's why we use it in balloons. So very well done, everyone. And what about argon, xenon and krypton? Why are they used as shield gases? So I should say that as a shield gas, they're protecting metals. So why are they used as shield gases? What does that mean? What properties do they have? This one's slightly more tricky to understand. Yep, excellent. So because they're unreactive, they can be used as shield gases. So the main thing with these argon, xenon, and krypton protecting these metals is that it stops them corroding. So remember that a lot of metals can react with oxygen and corrode and rust. And if we want to stop those, we can use these non-reactive noble gases. And what they will do is they will protect that metal from reacting with oxygen. And the reason here is because they are more dense than air. So helium is less dense than air, but argon, xenon and krypton are more dense than air. So remember that density increases down the noble gas group. So if we have a look, helium's at the top, but argon, xenon, and radon are, argon, krypton, and xenon are lower down. So they have a higher density, and specifically, they have a higher density than air. And what that means is they can stop the oxygen reacting with the metals. And also, because they're unreactive, they themselves won't react with the metals. So there's twofold. So first reason is that because they're more dense than air, they stop the oxygen reacting with the metals. And the second reason is because they are themselves unreactive, they won't react with the metals. So radon is a radioactive noble gas, so it's very rarely used because it's not safe. It's the only radioactive noble gas. Okay, so let's do some questions then. So before we move on though, does anyone have any more questions about noble gases? Okay, so let's go on to a question. Oh, what does react with noble gases? Very good question. So actually not a lot of things react with noble gases, and it's very hard to get them to react. For the purposes of the exam, you can just say nothing reacts with noble gases. That's absolutely fine, because for GCSE purposes, you don't need to know anything that does react with noble gases. And if I'm honest, there aren't many things that do react with noble gases. And yeah, it's very hard to get them to react. In all noble gases, can all of them not bond with other atoms? So no, they don't bond because they've got that full outer shell of electrons. That means that they don't have any electrons to share, lose, or gain. So remember, when elements react with each other, there has to be some kind of transference of electrons. So remember, reactions are always to do with electrons. But in the case of noble gases, they don't have any electrons to share, lose, or gain. So that means they're non-reactive and they won't react with other elements. Okay, so here's our first question then. Explain why ethanol and water can be separated using fractional distillation. So right back to the beginning of today, what did we cover? Why can they be separated? So someone's asking, what about radon? What's its use? It's radioactive. It's not really used. It can be used in medical equipment, but again, it's very dangerous. It's radioactive. So they have different boiling points. Excellent. So that's one of the reasons. Someone's saying it's easier to separate and you can form a purer sample of ethanol and water as it has a higher boiling point because ethanol has a lower boiling point. They are miscible. Excellent, really good answers to that question. Very well done. So yep, the main things are that ethanol and water are miscible, so can be separated using fractional distillation. They have different boiling points. Specifically, ethanol has a lower boiling point than water, so will evaporate at a lower temperature, and that means when it enters that fractionating column, it will condense, whereas if the water vapors enter that fractional distillation column, it will drip back into the round bottom flask because it condenses at a higher temperature. And remember, there are higher temperatures at the bottom of that fractionating column, so it means due to gravity it drips back, whereas the ethanol will condense at a lower temperature, and therefore that will be higher up the fractionating column. Okay. Explain why you would be able to collect a more concentrated sample of ethanol from a mixture of water and ethanol using fractional distillation than by simple distillation. So we did look at this today. What's the reason? Does anyone remember why we use fractional distillation and not simple distillation? Yep, it's to get a purer sample, and that's simply because if we use simple distillation, what will happen is that we will get a mixture of water and ethanol, even though we want to separate the ethanol from the water. And that is because the difference between boiling and evaporation. So remember, if we know that the boiling point of water is 100 degrees, that doesn't mean it starts boiling at 100 degrees. That means it can start evaporating before 100 degrees. At 100 degrees, all of water will become a gas, but at, for example, 85, some liquid particles of water will come to the surface and start evaporating. So the fractional distillation column prevents that water vapor from entering the condenser. Instead, it makes it drip back into the flask, whereas in simple distillation, there's no fractionating column. So those water particles that have started to evaporate before the boiling point, they will effectively end up in our separation of ethanol and water, which we don't want. We want pure ethanol. So exactly correct. Well done, everyone. Okay, explain the purpose of argon in light bulbs. Why do we use argon in light bulbs then? So we've got to apply what we know about our noble gases. Why do we use argon in light bulbs? Okay, so someone's saying unreactive, well done. Okay, excellent. So someone's given me a really good answer here. They've said it doesn't react with filament like air, with the filament like air would, and it's more dense than air, so the filament does not react. Well done, really good. So most filaments are made of tungsten. Again, you don't need to know that. That's just if you want to know. They're made of tungsten, and tungsten will corrode if it reacts with oxygen. So to stop that, we put argon gas in light bulbs, and what that means is, as people have said, it's more dense than air. So it will shield the tungsten filament from corroding. And so that means there's no oxygen in there, so the tungsten cannot react with oxygen and corrode. Instead, the argon gas protects it. And again, the second reason is that argon is unreactive, and so therefore it itself will not react with the tungsten filament. Well done. Okay, so the next question is about chromatography. Before we move on to that, we've got a few questions. So why can't we use neon? Again, so neon's mainly used in car headlights. Does anyone know why neon's used in car headlights? What's the purpose of neon being used? Yeah, it's bright. So neon is really bright. So one of the main purposes of neon is in car headlights, whereas argon, radon, and not radon, argon, krypton, and xenon are used in filaments and things and light bulbs to protect metals. You can still use neon. It's just it's not its main purpose. Again, I think it's to do with the fact that if we have a look on our periodic table, neon is probably less dense than air, and argon, krypton, and xenon aren't. They're more dense. So it's to do with the densities. Okay, so let's look at an exam question on chromatography. So the result of a process used to detect and identify the colours in two foods, A and B, is shown. Describe the differences between the colours used in food A and food B. So what can we see then? How can we describe that then, the differences between the colours used in food A and food B? And so 2 marks, so we need 2 different points. Okay, so A has more colours, 4 compared to 3. Excellent, so that would get you 1 mark. What else? A lot of people are saying food B is more soluble. We can't infer that from the chromatogram. Just because it has 3 substances that look a bit more soluble, we can't really infer that. Okay, so we've got 1 mark so far. We've said that food A has 4 colourings in and food B has 3. And great, so the second mark would come from the fact they share 2 substances. So there's 2 substances they share, this one and this one. So 1 mark comes from food A has 4 colourings in it and food B has 3, and they share 2 colourings. That's the second mark. Okay, so I've said already what this process is, but what's this process called? Yep, chromatography. Well done. Okay. All right, so we've got another one then. So W, X, Y, and Z are food colorings that may cause hyperactive behavior in young children. A scientist used chromatography to see if these food colorings were used in 2 sweets, S and P. The results are shown on the chromatogram. Food colorings such as W, X, Y, and Z are added to some sweets. Suggest one reason why. So does anyone know why do we add food colorings to sweets? Excellent, really good answer. To make them more attractive. Yep, that's pretty much the only answer that examiners are looking for there. So it does make them more attractive. Yep, so if we didn't use food colorings, they might not look as attractive as they do or as appetizing. Excellent, very well done. Okay, so someone was asking me before about RF. So in chromatography, the RF value is, remember, distance moved by the colouring and distance divided by the distance moved by the solvent. Use the scale on the chromatogram to help you answer this question. So I've not got a ruler, but we can have a look. So which of these ones do you think, W, X, Y, or Z, has 0.7 as a retention factor. We've got a scale here. Remember, it's the distance moved by the food colouring divided by the height reached by the solvent. So out of W, X, Y, or Z, which one do you think will give us a retention factor of 0.7? Okay, so we've got a lot of answers coming in for X. Excellent, well done. That is the correct answer. So it is X there, and we can see X here is at 7. This is X. So that means 7 divided by 10, which is the height reached by the solvent, would give you a score of 0.7. So that's an example of retention factor there that they could give you in the exam. So someone's asking, how do we get that? Again, so we look at the 4 dyes, and they've helpfully given you a scale. So remember, the retention factor is how far it moved. So for example, W moved 3, Y moved about 6, and Z moved less than 1. So let's just say about 0.5. And then we divide that by the height reached by the solvent. Do substances have the same RF value given human error? Yes. So human error is always something to take into consideration here. But in an exam question, they might ask you one of the limitations. You could say human error. But for RF here, it is X that has 7. And so we do 7 divided by the height reached by the solvent, which is 10. 7/10 is 0.7 as a decimal. Okay, well done, everyone. From the chromatogram, what conclusions can the scientists make about the colorings in sweet S and sweet P? So we want to know about the colorings in sweet S and sweet P. What conclusions can be made? So again, very similar to the question we just did. What conclusions can be made? Someone's asking, why did we divide? So that is the equation for retention factor. So we look at how far a substance moved, and we divide it by how far the solvent moved. So that's the equation for retention factor, because remember, retention factor is about solubility, and we know that the distance a substance moves is how soluble it is. So if we look at the retention factor, it gives a numerical value for the solubility. Okay, sweet S has more food colouring than P. Excellent, yep, so it has 6 food dyes in it, whereas P only has 5, so that's 1 mark. What else? Both contain food colorings W and Y. Excellent, really well done. So here's W, we can see that's in both, and we can see Y is in both as well. Yep, really well done. Both sweets are almost identical. Okay, so I'd be careful about saying they're almost identical, because that can be a bit difficult to infer. So again, I would stick to 2 things when you're answering these questions. How many dyes in each sweet, and are there any overlaps? So someone said W and Y are in both, so that would be enough to get you your marks there. Well done. Okay, again, paper chromatography is one method of testing which colours are in cake icing. Why is there a lid on the container? So why do we have lids on? What do we think? What does that protect? Excellent. Someone's saying to prevent evaporation. So it's exactly like when we draw our gas. So when we draw gases in states of matter, remember we always put them in sealed containers, and that's because gases can evaporate. So same thing here, the solvent could evaporate. So that's why we put a lid on. Well done. The start line should be drawn in pencil, not in ink. Suggest why. So we covered this earlier. Why do we draw the start line in pencil and not in ink? Yep, ink smudges to prevent it dissolving in the solvent. Excellent, both are absolutely fine. So pencil's not soluble, so we use pencil. Very well done, everyone. Good, okay. How many different food colourings were used in the colouring from the cake icing? Good, 4, exactly. So 1, 2, 3, 4, well done. Is the cake icing safe to eat? What do we think? Someone's saying yes, some people are saying no. We've got about 50-50 at the moment. Some people are saying, okay, so we've got 50-50. All right, so it says that the safe food colours are this one, and this one. If we look at our chromatogram, we can see that it's got one of the safe food colourings, it's got the second safe food colouring, but the third and fourth food colorings are not one of the safe ones. So what that means is that actually it's not safe to eat. So well done for everyone that said no. For the people that said yes, just remember to look at the chromatogram and have a look at what it's saying. So it says these are the safe food colors. So that means these two over here are not safe. They're not one of the safe ones, so we have to say no. And the reason for that is that it's got two colorings in it that aren't part of the safe food colors. Okay, so we're not going to cover gas chromatography. All right, before we go on to the Q&A, let's have a go at this question. So this isn't chromatography, it's about filtration. And another one, so it's about yesterday's topics. So the diagram shows a water filter used in the home. A student collected a sample of water from the filter. The student could show that the filtered water contained dissolved salts without using a chemical test. So how do we show something contains dissolved salts? What's the method that we use there? Okay, someone's saying filtration. It's not filtration. How do we show something has dissolved salts in it? Crystallization. Excellent. Well done for people that are saying crystallization. So just like the question we did right at the beginning, exactly the same here. So how do we do crystallization? What do we need to put in this answer then? If it's so, remember, crystallization is not a chemical test. So it is a physical test. Does anyone know why we count it as a physical method? Why all the methods I've taught today and yesterday are physical methods and not chemical? Yep, there's no reactions going on. They're just separations. Excellent. Okay, so we heat up the solution. Great, so that's the first thing. Good. Okay, so what else do we need to do with crystallization? So we heat up the solution. What are the next couple of steps? What do we heat? Yeah, we use a water bath and a Bunsen burner. Excellent, very well done. Anything else that we can think of that we do? Someone's asking, what exam board is this based on? These are all exam boards. All of them have crystallization, filtration, and distillation in them. So remove when the crystals start to form and transfer to a Petri dish and heat until the crystals start to form. Excellent. So these are all important answers for this question. Okay, very well done. So we'll move on to the Q&A now, and then if we've got time, we'll do some more exam questions.
Great, thanks, Aman. Just having a look through at some of the questions that have come in. Someone has asked, what is chromatography?
What is chromatography? Okay, that's a great question. So it's used for separating things like dyes. So if we've got a mixture and it's got different colorings in it or different substances in it, one of the ways we can do that is using color. So as I said at the beginning, let's say that we've got a message written in a certain ink and we don't know which pen was written to write that message. So things in forensics. And we've got 3 different pens that could have been written. Could have been used to write that message. We can use chromatography to separate those 3 inks as well as the original message and see which chromatography map, if you like, matches with the original ink. So if I go back to a question here, for example, so if you imagine here we've got sweet S and it's got 6 different colors in it, and we've got different food colorings and we want to know which food colorings are in sweet S, we can see that sweet S contains W because they match, and Y. So it's used to kind of separate what substances are in kind of things like sweets, things like messages. It's all about inks and colorings.
Great, thank you. What level would a density equals mass over volume be in GCSE?
That's a very good question. So at foundation tier, you just need to know kind of that density equals mass over volume. You wouldn't, in GCSE chemistry, you aren't expected to be able to calculate density. You're just expected to kind of know the properties of molecules and why they have that. So for example, the noble gases have an increase in density as you go down. That's a higher tier thing, but you do need to know what density is. You wouldn't be expected to explain why the density increases down the noble gases.
Okay, and in all noble gases, can all of them bond with other atoms or not?
Yeah, that's a great question. So no, they don't bond with other atoms, and that's because they have the full outer shell of electrons, so they are non-reactive. And because they're non-reactive, that means they can't share electrons, gain electrons, or lose electrons. So remember, when bonding occurs, there's always some kind of electron transfer going on. But because noble gases have a complete outer shell of electrons, which is what all elements want, they don't take part in any reactions like that, so they don't bond, and that's why they go around as single atoms as well.
Is the method for gas chromatography and DIY chromatography the same?
No. So gas chromatography, as I said, is a higher tier topic that we will potentially be covering in later weeks. It's not in all the exam boards, so we may not cover it. DIY chromatography is very different. Gas chromatography is done within a, you do it at school, but again, it would be done at A level. You wouldn't do it at GCSE, so they're different things.
Can you please explain what RF is?
Yep, so RF is the retention factor. So the question that we're on is a great example of that. So I'm just going to change my pen color. So if we have a look at X, we can see that X on the scale has moved to about 7. So it doesn't have a unit on it. That's absolutely fine. We don't need units for retention factor. So that means if it's moved 7, we want to know how soluble X is. So we basically do that as a fraction, 7 over how far the solvent moved. So remember, a lot of things are put in a solvent. So for example, these sweets might be put in a solvent of water, someone put in a solvent of ethanol, and we can see how far the watermark moves. So if the watermark finishes here, that's the height reached by the solvent. So the retention factor would be 7 divided by 10, and that means 0.7. So that means 0.7 is more soluble than, say, Y, which has moved about 6 or 5.5. And that means we do 5.5 over 10. So again, that's about 0.55. So that is less soluble than X. So Y is less soluble than X. So retention factor is to do with how soluble a substance is, and it just puts a numerical value on it. Someone's asking me, can you please explain stationary phase and the other phase? Yep, really good question. So with chromatography, the mobile phase is about these substances moving. So these dyes moving up, so they're the mobile phase. The stationary phase is the paper. So the paper is stationary, it doesn't move, and it's about, in chromatography, you've got the mobile phase, which is the substances moving up the paper, and the stationary phase is the filter paper.
Okay, someone has also asked, what other mixtures can you separate with fractional distillation?
So for GCSE purposes, you need to know that you can separate ethanol and water and crude oil. They're the two that we need to know about.
Okay, I haven't seen any new questions come in. Oh, someone's just asked, if the dye moves up the paper with more distance, then does it mean it's more attached to the mobile phase?
It means, yes, so it means it's got a higher, you can say attachment to the mobile phase, so it's more soluble, whereas if something moves less far up that paper, yes, it's more attached to the stationary phase.
Great, and while we wait for some more questions to come in, can we do another paper question, please?
Yep, that's absolutely fine. So chromatography can be used to separate components of a mixture. A student used paper chromatography to analyze a black food coloring. The student placed spots of known food colors A, B, C, D, and E and the black food coloring on a sheet of chromatography paper. The student set up the apparatus as shown in diagram 1. The student made 2 errors in setting up the apparatus, identified the 2 errors and described the problem each error would cause. Can anyone see any errors in the apparatus on the screen? While we're waiting for that, someone's asking what topic are we doing next? So tomorrow we'll be covering group 1 and group 7, the groups in the periodic table, and on Friday we'll be covering the transition metals and then a quick summary of everything that we've done this week. So we'll be just doing the periodic table for the rest of the week now. Someone's asking, would they show the RF line, the RF equation in an exam? Yes, they would. Okay, so as answers to this question, the 2 errors, some people are saying the line is drawn in ink and the dots are in the solvent, not above. Okay, yep, so they are the 2 errors. So what happens then? If we put the line in ink and not in pencil, what does that cause? So we've got to describe and we've got to explain what that does. Look, it says describe the problem each error would cause. Good, so the ink gets smudged or gets dissolved in the solvent. So that's one thing. So the ink line should have been drawn in pencil. And the second reason, what's the second reason that people are suggesting here? It says, so some people are saying solvent starts above the start line. So what's the problem with the solvent starting above the start line? The dots won't move up the paper. Yep, why don't the dots move up the paper if the solvent starts above the start line? Yep, the ink won't be able to move as it will have dissolved. Well done, everyone. Good, so that's the two errors and we've described those. Just before we move on to the next question, someone's asking, will we be covering reactive metals? So group 1 are the reactive metals, we'll be covering those tomorrow. And transition metals are also not as reactive, but some of them are quite reactive, and we'll be covering those on Friday. Good, okay. So a different student set up the apparatus without making any errors, and the chromatogram in diagram 2 shows the student's results. What do the results tell you about the composition of the black food colouring? So what can we say about the black food colouring? Someone's asking, will we be doing the history of the periodic table? No, so we did a bit of the history of the atom last week, but we won't be doing the history of the periodic table. Just because we had one less day this week, so we couldn't cover that. So I thought we'd just do the more kind of the harder topics to understand, which are the things about all the groups and the periods. Okay, so it contains food colorings A and E. So yep, the black food coloring is made of A and E. So we can see A matches in the black food coloring and E matches in the black food coloring. Well done. Anything else? Remember, 2 marks there, so you get 1 mark for saying that it's made of A and E. What else? It has 3 substances in it. Well done. Okay, use diagram 2 to complete the table. So we can't do that, but this would be how you would be asked about the RF in the exam. So remember, it's the distance from the start line to the solvent front, and the distance moved by food colour C. So this is the solvent front. So we would take a ruler and we would measure where it is the solvent front, and then the distance moved by food colouring C, and we go to the top of food colouring C. So you go to here. And then the RF would be 1, so C divided by the solvent front total. Okay, so that's the end of the exam questions that I have. Someone's asking, what websites do you recommend to visit when getting a start to A-level chemistry? That's a really good question. So what I personally did was I bought the CGP book. So CGP have a book called Getting a Head Start to A-level chemistry. That's really good because it's a nice kind of crossover from GCSE to A-level. It's not too difficult to understand, and it kind of gives you kind of a basic understanding of some of the key topics that you'll cover at A-level. Website wise, so there's things like physics and maths tutor that have a lot of chemistry kind of resources on there, and there are now online textbooks that you can buy. They're a lot cheaper than physical textbooks, but I would be wary about buying an A-level textbook because it can be quite overwhelming. So that's why I think that kind of head start to A-level chemistry book that I was talking about is a lot better. It's kind of just, it covers a bit of the GCSE stuff and goes into the A-level things as well. It's like a nice bridge between them.
Great. And if we don't have any more questions, then I think it's a good place to leave it there, because we're almost at the hour. And just to say to everybody that it has been recorded, and if you have signed up to the My Tutor online school, then you should get a link linking out to the video afterwards. So thanks everyone. Just a reminder that we still have English at 11 o'clock today, and we also will have maths on as normal at 12:15, and in case you didn't know, we have physics at 2 p.m. and we then have a history webinar at 3:15, which is our first history one. So stick around for all of those. Thanks everyone, and see you later. Thanks, Aman.